All right, well, good evening. This is Engr124, lecture on mass flow rate and applying the first law to diffusers and to nozzles. So hopefully you have a sheet of paper where you can take down some notes and basic equations. You have your tables, and we'll do a couple of examples to get some practice with this. So let me jump right into it, and then I'll talk a little bit about how this relates to the work we're doing this semester in Engr124. So first thing, working with mass flow, before you do this video, you should have completed the part A or the part 1 of homework number 8. And on that homework, I asked you to look up in the book some very basic equations on mass flow, really mass flow, speed, and volumetric flow rate of fluids. Quick reminder on those. A lot of times, the problem solving we do in this class, we need mass flow rate. In reality, if you work out in the field, you're not going to have a meter that actually is going to come up with kilograms per second to mass flow rate or pound mass per minute. Instead, you're going to have some sort of device that actually measures volumetric flow rate, things like gallons per minute, liters per second, meters cubed per second, cubic feet per minute. So a lot of times we start with volumetric flow rate. Quick reminder, the book symbolizes it with a V with a dot over it. So volumetric flow rate, that would be something like meters cubed per second. And what if we want to actually get mass flow rate? Well, if you took meters cubed per second and multiplied it by kilograms per meter cubed, that's going to give you mass flow rate. And what I did there was I took the volumetric flow rate and multiplied it by the density. So one equation we have is our mass flow rate is our volumetric flow rate multiplied by the density. Of course, density and specific volume are reciprocals, so another way we could do it is we could do the volumetric flow rate divided by the specific volume. So those are two really basic equations that you should have in your repertoire if you're doing problems with flow. Another thing that we're interested sometimes is, well, how fast is the fluid moving? 10 meters per second, 2 meters per second, 3 feet per second, etc. So again, we're starting with volumetric flow rate. And as many of you know from your fluids, you can get the average speed of a fluid by taking its volumetric flow rate and dividing it by its cross-sectional area. So let me get those two formulas up there. So once again, you imagine that you have a fluid, say, entering a pipe, and you're wondering how fast is it going? Well, to get the average speed, you can take the volumetric flow rate and divide it by the cross-sectional area. All right, so that is another basic equation. Of course, it can be rewritten in a form where it doesn't have a fraction, as volumetric flow rate is average velocity times cross-sectional area. So those are three basic equations that you should have in your repertoire. The last thing is that we can combine the mass flow rate equation with the volumetric flow rate to get a single equation that's very useful too. Is mass flow rate is density times average velocity times cross-sectional area. Let me just write one more thing up there, and I'll show you in just a second. Okay, so last set of equations. Our mass flow rate is our density times our average velocity times our cross-sectional area, and because density and specific volume are reciprocals, we can do average velocity cross-sectional area divided by specific volume. Okay, and that's stuff that you should have practiced with a little bit on the first part of homework number 8. All right, the next thing that we want to be able to do is apply those equations to devices that are at steady state. Okay, in steady state, there are a couple things we talked about it. One is that the energy level is neither rising or falling. And the second thing is the mass level is neither rising or falling. So I'm going to just draw a quick example of a steady state system. Okay, so here I've got a system, and it's a pipe, and fluid's entering it at 2 kilograms per second. So by the way, that's actually a pretty big mass flow rate. All right, well, what rate should fluid actually come out in that case? Hang on for a second. What rate should fluid come out? Well, if it's at steady state, the amount of mass within that system cannot be changing, so it's got to be 2 kilograms per second out. Mass in and mass out have to be the same. Okay, we already knew that. What, in addition, becomes helpful is to write the equation m dot in equals m dot out using the relationship for mass flow rate that we had a little while ago. And mass flow rate can be gotten by multiplying the density times the volume times the cross-sectional area. So we could get an equation for in equals out, or we could also use subscripts 1 and 2, where 1 would be the entry, 2 would be the exit. And let me write it out really quickly. Okay, so a really useful equation. If I have a fluid flowing in, the product of its density, its inlet velocity, and the cross-sectional area where it enters, and the density and the velocity and the cross-sectional area where it exits has to be the same. Okay, we're going to use that in just a second in a little bit more complicated situation, but let's start with something really easy. Let's see what that equation says for a fluid entering a pipe and the fluid's incompressible. So I have some fluid entering the pipe and it exits the pipe. If it's incompressible, that means the density at the entrance and the density at the exit would need to be the same. Okay? If it's a pipe of constant cross-sectional diameter, the area the whole way along, the cross-sectional area is the same, this area and this area would be the same. And let's see what that says. If these two densities are the same, we can cross them out. If these two areas are the same, we can cross them out, and we get V1 is equal to V2. Okay? So what that's telling us is if we have a pipe with an incompressible fluid, constant diameter, the velocity, the average velocity is the same. If some water inserts here at 10 feet per second, it's going to exit there at 10 feet per second. All right, basics. Let me just write one more version of that equation, and that just involves this equation right here that hopefully you wrote down a little bit earlier. Okay, and that is to rewrite the density as 1 over the specific volume. So I'll get that up there in just a second. Okay, so in general for steady state, our total mass flow rate in and total mass flow rate out have to be the same. That can also be written with this density formula. And finally, it can be written in terms of specific volume. V1A1 over the specific volume at the inlet is equal to V2A2 specific volume at the outlet. All right, good. Okay, so before we apply to diffusers, let me just talk for just a second about using this video. I really encourage you when we get a problem on the up on the whiteboard to work just like we're in class. Push pause, get as far as you can, and then you can every now and then go through the video and make sure you're doing your work correctly. If you do this practice, it's really going to help you out. Second thing, just to talk about really briefly, hey, I know it's been a rough couple weeks with here at Sac State, and of course it's been horrific up in Butte County with the fire going on. So we're all just hanging in there trying to do the best we can. We'll see you all on Monday. As far as what you're responsible for regarding these videos. Last week, the campus, President Nelson said, hey professors, even though you'd like to post videos to keep your students along, you can't do it. This week, the instructions were ambiguous. I actually emailed the president's office and they said it was okay, but I'm really unsure whether it was acceptable to do this. I believe it's okay, but not sure. So what I'm doing is posting these videos in part because I want to give you a course that exposes you to the basics. I am not going to test you on the type of systems that we're doing in these videos. We're going to do it. We're going to do a nozzle and we're going to do a diffuser. So if you feel like, hey, this is not working out for me, I don't have to do the time to do this, you get through homework number 8, part 1, you're good to go for test 2. On the other hand, I do want to say that any additional you do with equations or concepts helps with this course. So if you have the time, I'd really encourage you to go through and do this work and do the couple additional problems that I added to homework number 8 for homework number 8, part 2. All right, enough said. Let's go ahead and do a nozzle problem and take a look at it. Give me just a second to erase. So nozzles. are something that can be analyzed using the equations we just developed. So I'm going to get a nozzle up there. A nozzle is just a section in a pipe where the pipe narrows. Okay, and we're just going to take a look and see what the outlet velocity actually is for a nozzle. So I'm going to get some really, really typical numbers up there. And give me just a second and I'll have you write it down yourself. Okay, so in words, this would be, hey, what if we had a flow situation where we had some fluid going at 10 feet per second, and it was entered a 2-inch diameter nozzle, and the nozzle narrowed to 1/2 inch? What would the outlet velocity be? Okay, well, hopefully your intuition would lead you in the following direction. Let's say this is water or some sort of incompressible fluid. I should have said that. This is for an incompressible fluid. Well, there's less space for it to get through as we go down through that nozzle. There's less space. That water needs to speed up so that it can actually all the water that enters can exit. There's less space to get through. So if the same amount of water in, the same mass flow in, and the same we have to have the same mass flow out, that water needs to speed up. All right, how about putting a number on it? That would make us do some sort of be more like engineers. Well, what we can do is we can use the equation that the mass out and the mass in have to be the same. That has to be true if this is a steady flow situation. Okay, so this problem, if it was laid out in more detail, was that, hey, you have a nozzle operating at steady flow, 10 feet per second in, what's the velocity out? Okay, well, if it's steady flow, the mass flow rate out and the mass flow rate in have to be the same. Okay. Well, we can take that equation and rewrite each mass flow rate in terms of density, average speed, and cross-sectional area. So I'll write that next as the next step. Okay, so there's our equation, and that's looking pretty good. It has V2 in it, what we're looking for. We're looking for the outlet velocity. And let's just go ahead and think about solving. First thing is there anything we can eliminate? Well, if it's incompressible, that would mean that the density doesn't change. We can't decrease its specific volume. It's a fluid that the specific volume or the density is constant. That makes it a lot easier. We can cross out the two densities. Okay, and then we can solve for V2. That's easy enough. It looks like we have enough information to get the area. So let me write that next line in. By the way, if you know what you're doing, just go ahead and finish this off on your own and see if you get the right outlet velocity. Okay, so crossing out the densities, I solve for V2 and I get V2 equals V1 times the ratio of the inlet area to the outlet area. Note that in Engr124 and probably in your fluids class, for a cross-sectional area of pipes, instead of using pi r squared, a lot of times we use pi d squared over 4. That comes from the fact that pipes are usually specified in engineering in terms of diameter, not radius. Okay, well, let's just go ahead and start filling in. Once again, I really encourage you in your engineering work, do as much simplifying as you can first and then fill in the numbers. So I'll write, try to finish this off on your own and see if you can solve for V2. Okay, so I've filled in the pi d's, and hopefully you see that both the pi's, there's a pi in the numerator, pi in the denominator, a 4 in the numerator, 4 in the denominator, so those go away. So we can just express it as follows. Okay. The outlet velocity, V2, is equal to V1 times the ratio of D1 over D2 squared. And that's going to work out really nicely because all the units are going to cancel out and we should get the units we want. So let me try to finish that off and you guys do that yourself. Okay, so I filled in my diameters. There's no need, excuse me, sorry about that. There's no need to convert to feet because the inches are actually going to cancel out. 2 over 1/2 is the same as 4. Square that, 16. So we're going to have an outlet velocity of 10 feet per second multiplied by a factor of 16. And so it's an outlet velocity of 160 feet per second. Okay, so just by taking some water and forcing it through a nozzle where the diameter actually ends up changing, going from 2 inches to 1/2 inch, we get a huge increase in velocity. I cranked through those numbers just before I did this, and if I did my conversions right, I got an inlet speed of 6.8 miles per hour, so that's moderate, and coming out at about 110 miles per hour, so it's really flying on the outlet. Okay, good. Another thing I'd like you to just think about is, hey, what would be going on with temperature with this water right here? Would the temperature at the outlet and the temperature at the inlet be the same? Well, to do that, we might need to think about some different relations we have. And one relation we actually have is our conservation of energy. And we could use that. We won't do that, but it will turn out that there's not much change in temperature. And part of that has to do with the incompressibility. The situation gets a little bit different, though, if instead of using an incompressible fluid like water, we use a compressible fluid like a gas, like air. And that's what we're going to do in the next example. So give me a second to erase the board, and I'll start talking about it. What we're going to do is a similar situation, a diffuser. Okay, diffuser is the opposite of nozzle. And we have some fluid entering through a narrow opening, and then the device, the diffuser, it actually expands. So it would look something like this. Give me just a second to draw it for you. So we're going to have an inlet that's pretty narrow. Okay, and once again, the book does a lot of the different devices in Chapter 5. All this is in Chapter 5 with trapezoids. So I got a trapezoid, and I have this fluid coming in here like this. And then as it goes through, it has the ability to expand. You would think that a fluid might go in a straight line because a fluid's a particle, and particles follow Newton's first law. They like to flow in a straight line. But at the same time, gases tend to spread out and fill available space. So these fluid lines will actually end up expanding outward as it goes through the device, and will end up coming out here like this. So just check your thoughts for just a second. If I had a fluid going through a diffuser, speed up, slow down, or could it possibly stay the same speed? And it's the opposite of the nozzle. There is more space for it to emerge, and it ends up the gas or the fluid ends up spreading out, so it ends up slowing down as it goes through there. All right, so I'm going to get a typical example up there, and we're going to think about how we're going to wind our way through it. I'll describe it really quickly while I erase it. So we're going to do air on this one, okay, and we're going to have air entering an adiabatic diffuser. So you might want to write that down. I'll get that up here in just a second. Air enters an adiabatic diffuser. Okay, and we're going to have it going 200 meters per second at the inlet. Okay. It's going to be at 80 kPa. Okay, and it's going to be at 17 degrees C, which is about 63 degrees Fahrenheit. Okay. The inlet area of this diffuser is 0.4 meters squared. And our question is going to be, one more bit of information. It exits at a slower speed, so we're going to do 10 meters per second. Okay, so there's the problem description. I'd like you to just think about it for just a second. There we go. Okay. And what I'd like you to do is draw the diffuser and see if you can get that information up there. Get the inlet state and get the outlet state, and then we'll talk about the two questions. So you're going to draw the diffuser as a section of as a trapezoid, and get the inlet information and the outlet information at the correct space. Okay, good. All right, so there's my drawing of the diffuser. I got a trapezoid. I have it oriented correctly, and I got the air coming in at 200 meters per second and exiting at 10 meters per second. So, by the way, when would a situation like this actually come up? Well, it turns out that a lot of jet planes take in air, and then they actually use that air to go through a turbine to accelerate to help move the plane forward. And if a plane is flying really fast, well, it might be flying at 200 meters per second, and that inlet air might be too fast actually for the turbine it's going to go through. So by going through a diffuser, the air slows down to a speed that's acceptable for a turbine. Okay. So the things that we're going to calculate in this case is we're going to try to get the mass flow rate at the inlet. How much mass is going through there? And then the second thing we're going to try to do is get the outlet temperature. So first thing to do, okay, mass flow rate at the inlet. So I'll let you guys think that for a second. At this inlet here, how are we going to get the mass flow rate? All right. And hopefully you can go back to those equations that we have earlier, and I'll write them up there. Write a basic equation up there. Okay. So those are two good choices for us to get the mass flow rate at the inlet. Maybe I could have called it m.1. Taking a look at the information that we had, we do know that velocity at the inlet. The velocity at the inlet is that 200 meters per second. Okay. We can't figure out the area at the inlet because that's given. That's 0.4 meters squared. So then the question is, how are we going to get either the density or the specific volume? So you might, pull out your equation sheet, look through this, something that you should keep working on. Before you give up, go to your equation sheet. And a hint is this is a gas. Air is a gas, so we could use the ideal gas law. So let me get that up there, and we'll see if we can work that out. Okay. There is one form of the ideal gas law. PV equals RT. PV equals RT. So could you use that to get the specific volume? Well, if you think about what's given, absolutely. You could solve that for V and you get the specific volume. The one bit of information you would need would be the R value for air, and you can look that up in table A2. So let's go for it. Let's go ahead and get the specific volume and see if we can finish that off. We'll get the board up there for you to look at in just a second. Okay, so there it is, filled the ideal gas law filled in. 0.287 is the gas constant for air. 290 is air's temperature converted to Kelvin, and 80 kPa is the pressure. You might look and say, wait a minute, why is the pressure 80 kPa if this is an airplane flying through the air? And we've said in class that atmospheric pressure is usually about 100 kPa. Well, what's going on is maybe this is flying at a fairly high elevation. So the higher you go up in the atmosphere, the lower atmospheric pressure is. So 80 kPa would be an appropriate pressure for a fairly high elevation. Okay, hopefully you crank through that on your calculator. I'll do that myself. And again, our goal is to get the mass flow rate. So let's see if we can finish that off. All right. So the specific volume of the air is 1.04 meters cubed per kilogram. I didn't go through and do the work to show that the unit simplified to meters cubed per kilogram. But if you can remember that a kPa is a kilonewton per meter squared and a kilojoule is a kilonewton meter, then it works out really easy. Okay, so what are we trying to do to finish it off? We're trying to use this m dot equation up here, and we're using that expression right there. So we're going to fill it in and see what kind of mass flow we get. So I encourage you to stop for a second and see if you can work it out yourself. So if you're working it, those are all the numbers filled into the formula. And if we crank through it, hopefully you can see that we're going to end up with kilograms per second. And we'll see what we get numerically. Okay, so my calculator cranked through to 76.9 kilograms per second. That is a lot of air. Remember, there's about 2.2 pounds per kilogram. And well, does that make sense? In this case, again, this is an airplane that's flying really, really fast. It's got a diffuser with a fairly large intake, 0.4 meters squared, and so a lot of air is going to go through it. All right. So the first question was, hey, what's the mass flow rate? The second question is, what's the outlet temperature? So why don't you give me a second to erase the whiteboard, and what I'd like you to do is think, okay, what are the different relationships that we have that would allow us to solve for the outlet temperature? So we could call that T2, the temperature at the outlet. I'm going to put a couple equations up there and we'll see if that'll work. See if they'll work. Okay, well, one tool that we want you to remember when you're working test 2 is the ideal gas law. So if we're taking a look at state 2 here at the outlet, and maybe we can use this equation right here to solve for T2. If you take a look at the information, though, given we don't have enough information, the problem doesn't give us the outlet pressure, it doesn't give us the outlet specific volume, you might look and think, wait a minute, we solved for specific volume in the first part, but the specific volume doesn't stay the same. This air is spreading out, so its specific volume is changing, and we don't have that information. All right, so can't use the first equation. Can't use this. What about this second equation here? Okay, well, let's take a look over here at the right side. P1, V1, and T1. Remember, in this case, V is volume, okay, or it could be specific volume. And we got P1, we got specific volume, and we got T1, so this is looking really good over here on this side. Okay, but what about over here on the left side? Okay, if we were trying to find T2, we would need to know the specific volume at the outlet, and we just said earlier we don't have that, and the temperature at the outlet, and the pressure at the outlet, and we don't have that. So we're not going to be able to use the ideal gas law. All right. Well, now we come to the really important thing, or really important part of the problem solving. Both what we want to be able to do in Chapter 5 is apply the first law to all sorts of different systems. The main two that we're looking at are turbines and compressors, but there are quite a few other ones in Chapter 5, and nozzles and diffusers are things we'd like to be able to do. So what I'd like you to do is just draw a control volume for the nozzle, and I'm doing that, and I'll show you in just a second. So what you're doing is you're drawing a trapezoid, dashed lines maybe to indicate where there can be energy transfers in or out, and I'll make the list. Excuse me for a second. I'll get it up there for you guys in just a second. Okay, so fundamental skill in this class is, hey, what are the transfers? What are the transfers in? What are the transfers out? So what I'd like you to do is think about those 6 possibilities. Energy transport by mass, energy transport by heat, and energy transport by work, and decide which, if any, of those are relevant to this situation. Okay, well, hopefully you'll see that for sure there's E dot mass in and E dot mass out, because there's air going to that diffuser and air going out of that diffuser, so I'll draw that in. Okay, let's go through the other ones. Let's go through heat transfer. Okay, could there be heat in or could there be heat out? Well, in reality, there could be a lot. Your diffusers need to be strong, and so a lot of times they're made out of metal. They're not necessarily insulated. In this case, though, it's assumed that the temperature differences aren't so great that there's not a significant amount of heat transfer. So if you look back earlier in the video, I said, hey, this is an adiabatic diffuser. So no heat transfers. Okay, how about power input or power output? So think back to compressors, turbines, pumps, fans, etc. Power input is when a lot of times when there's some sort of shaft that rotates and blades actually push on the fluid as it moves through the device. That would be true, say, on a compressor. Well, we don't have any of that, so it turns out that there's no power input. Power output, again, think of a turbine, some sort of blade with some sort of shaft with blades, and the fluid as it goes through, it pushes on those blades, and energy comes out of the fluid in the form of power output, and we don't have that either. Okay, so our first law basically just has two terms, mass flow in and mass flow out. So let me just go ahead and write the next line. What would that look like? Okay, m dot E in is equal to m dot E out. All right. So what I'm going to ask you to do is to try to keep moving through this equation and see if somehow it will allow us to meet our goal of figuring the temperature at the outlet. So what we want to do is probably do any algebra or simplification we can first and see how the equation works out. So first thing I'd like you to do is think about the m dots and think about how we actually write E, specific energy, for a flowing fluid. All right, so let's see what the next line looks like. I'm going to use 1 and 2, 1 for in and 2 for out. Okay, so a challenge for all you is to look at that equation and say, oh, I see that next line that follows from the previous line. So what's going on? Well, first of all, if it's a steady flow diffuser, steady flow device, the mass flow rate in and the mass flow rate out have to be the same. So those things go away. So our equation just basically says, hey, the specific energy of the air at the inlet and the specific energy of the air at the outlet have to be the same. Okay? And specific energy is a combination of the kinetic, the potential, and the H, and that's what I wrote in that equation. All right, now we're on to the next thing for you guys to work on. Can we eliminate any of those terms? For any of them, is there an insignificant change as we go through? All right, so let's start with velocity. Velocity at the inlet, 200 meters per second. Velocity at the outlet, 10 meters per second. Is that a significant change? Yeah, that's a huge change. So we're not going to be able to say these two terms are equal. So we can't do that. Okay, let's talk about the potential energy terms. All right. Well, if it's a plane, it's probably flying horizontally. So the level of this inlet and the level of this outlet are the same if it's horizontal. And even if it weren't horizontal, the change in elevation is going to be very, very small. So the elevation terms aren't going to be that different. So we're going to be able to eliminate those. Okay, how about the enthalpy terms? The enthalpy at the inlet and the enthalpy at the outlet. Turns out that those are not necessarily the same, and you can see it from what we talked about earlier. If this term right here has to equal that term right there, and if the velocity change is significant, then the H's have to change as well. So our equation for a diffuser is going to simplify to the previous equation I had on there with the GZ terms deleted, and I'll write it up there for you guys. Okay. I won't memorize this equation. Sometimes this is called the nozzle or diffuser equation for compressible fluids. There can be other variants of it, and I believe on the homework problem I asked you to look at a little bit of a different variant. But regardless, what we do want you to understand is that comes from conservation of energy, of saying that E dot, yep, the energy transported in by mass and out by mass is the same. Okay, well, how's that going to help? Our goal was at this outlet here to figure out the temperature, and it might be worth you pausing the video and taking a look at table A17 for a minute. Table A17. Hopefully you've done that. I'll talk about it really quickly. If we could solve this equation for H2, well, for table A17, if you know any value in a line, then you can find other values. So if you know H2, you can locate what our state of our outlet area is and get the temperature from that. So that's simple enough. Our goal in this case is to solve for H2. Why don't you try it yourself, and I'll be doing it on the whiteboard. Okay, so there's the algebra. H2 is going to be equal to H1 plus V1 squared over 2 minus V2 squared over 2. Okay, and then you can go ahead and go to table A17 and fill in the numbers. All right, H1 is the enthalpy of air at 290, which is 290.16. That's kilojoules per kilogram. All right, there we go. So I filled in H1, and then I filled in those velocities. And go through and compute those. These are actually going to be in meters squared per second squared, both of these. So I'll need to actually end up converting them to kilojoules per kilogram to finish it off. So try it yourself, and I'll be working on it as well. Okay, just to show you an intermediate step, this inlet velocity, kinetic energy, comes out to be 20,000 meters squared per second squared, and then I'm going to divide it by 1,000 because 1 kilojoule per kilogram is 1,000 meters squared per second squared. And I'll do the same thing with this 50, but hopefully you can see the way it's going to turn out. It's going to be 290 plus 20 minus just a little bit. So it's going to be somewhere around 290 plus 220, somewhere around 310. So I'll do that math myself really quickly. Okay, so you get the enthalpy at the outlet is 310 kilojoules per kilogram, and then we can go to table A17 and just by eyeballing get an approximate T2, and of course if we needed to be precise we could interpolate. So I'm going to look really quickly at my table, and it looks like that our temperature is around 310 Kelvin. If we wanted to convert that to Celsius, that's going to be 37 degrees Celsius, which is 99 degrees Fahrenheit. 99 degrees Fahrenheit. Okay, so hopefully that the logic of all that is something that you can follow. Again, on any of this stuff, feel free to email me if you have a question. The next thing to do is just talk about, hey, what's going on? Does that even make sense? So earlier I said that this entering air, let me look back at my notes, was at around 63 degrees Fahrenheit. Yeah, around 63 degrees Fahrenheit. And now this exiting air is around 99 degrees Fahrenheit, and that air warmed up. How could that be? What's going on with that? No heat, and yet it warms up. Well, if you take a look at what essentially this equation right here could be saying to us is, as it goes through, it ends up losing this kinetic energy, and that becomes enthalpy. That becomes actual energy of the air. So kinetic energy is lost, and it becomes enthalpy energy of the air. And enthalpy energy corresponds to temperature energy in a sense, and so the temperature actually rises. All right, that's it for this. That's it for this first part. This first bit. I'm going to do one more device with you. It should be pretty quick. Again, I think this additional work with devices is pretty helpful as far as practicing the concepts that we've worked on. Encourage you again to try those additional problems on the homework. Keep working and getting ready for next week. That is it for now. Thank you.